we have been discussing the consequences of Bloch's theorem, and we showed that Bloch's theorem makes life extremely simple for us in making the wave function obey certain symmetries, and it is just that the lattice transition symmetry gives us the nature of a function that you should choose for a solution. Now, on the basis of that, we did this we did a proof of the theorem, and we showed that you need to calculate the energy only in the region of a reciprocal lattice, which is called the first Brillouin zone, and then rest of it can be obtainable from that that spectrum in that region by just translation of a reciprocal lattice vector. Now, there is this other interesting thing that I mentioned, that this is called the hexagonal lattice, which is not a Bravais lattice, but as I said the previous day, that this lattice, of course, you can see that this point P and R are not equivalent. You can just check it, that P has a point here on the left hand side, upper left hand side, whereas R has no point at the center of this hexagon. Had a point been there at this center, then of course P and R would be equivalent, and the lattice would be a triangular lattice or a hexagonal lattice, as I showed in my previous lecture. So that means that this is not a Bravais lattice, but we can still work with it. The way to do it is to find out a unit cell such that this new unit cell with 2 atom bases becomes a Bravais lattice. So the choice of unit cell is also not unique in that, in the sense that here, for example, this is this region, this parallelepiped is this is the unit cell. So, for example, I can choose the unit cell in this way also, the yellow region here. So the red and blue are the 2 inequivalent sites. Although both of, in graphene for example, both of them are carbon, these sites are inequivalent. As I said in the previous graph, P and R are inequivalent, whereas P and Q are equivalent. View from P and view from Q are identical, whereas view from P and R are different. So so this is why it is there are these 2 types of sites that has been highlighted here by blue and red. Okay. Of course, and then you choose a unit cell in such a way that both one blue and one red type of sites are incorporated in the unit cell, and then you can repeat this unit cell to form a lattice, and that is you can check for yourself. This really gives a Bravais lattice. Then choose so for example, the central point of every yellow region, and then just add them, and you will find it's a Bravais lattice. Now, so in this case, there are this A1 and A2 are the 2 lattice vectors, primitive lattice vectors, and delta 1, delta 2, and delta 3 are the nearest neighbor vectors from any site to its nearest neighbors. One can then construct the reciprocal lattice, and this is the first Brillouin zone, is a hexagon again. Then the central point, as I say, is gamma, is basically k equal to 0, 0, 0 in 2 dimension. This point is along the x-axis, and this m point is gamma m is along x direction, no change in ky, whereas gamma So gamma k, for example, if you go in this direction, of course then you have to change both kx and ky. So mk, for example, is a vertical movement along this direction, ky direction. Okay, so these are the k and k prime are inequivalent points in the Brillouin zone, and so one draws the energy spectrum within this Brillouin zone along certain symmetry direction, as I said. So gamma m, gamma k prime, these are the directions in which one plots the energy spectrum, and from that you can actually figure out the nature of the energy bands of this kind of a system. We will come to that at a later stage, because this has a this is called a lattice with a basis. These kind of things can, as I said, is with a basis you can convert it into a Bravais lattice. Then again the Bloch theorem will work, and one should be able to derive the band structure for this kind of systems. Okay. So that's what I will try to introduce you now as to how to do. So remember your calculation for hydrogen molecule, and then I extended that calculation to include the for n number of atoms. I still remain in one dimension, but that can be extended to any dimension if there is a periodic arrangement. All you have to do is to change this vector, which is a one dimensional vector here, into a d dimensional vector if your lattice is in d dimension with appropriate Bravais lattice and corresponding primitive vectors. Okay. So this I said was for this kind of situation, our trial wave function, remember we choose our method was variational. So the trial wave function we chose was here was u1 plus u2 into, so here we will choose a trial wave function which is sum over I ui I, right? And then what we showed is that, for example, for a three-side problem, the matrix becomes epsilon naught and minus t, minus t, minus t, minus t, 0 and 0. So this is the matrix for u1, u2, u3 for a three-side problem, and this is equal to E times u1, u2, u3. Okay. So this is basically the equation that you will get if you extremize with respect to ui's, this energy, variational energy, which is E equal to psi h psi divided by psi psi. Okay. So this is the procedure that we have done exactly what we did for two-side problem, two atom problem. We can do it for 3-atom problem. We can go ahead and do it for 4-atom problem. There, what will happen is that you will have you have more zeros on this. There will be zeros, one more zero on the second row. There will be one more zero on the third row. So that's how it will go about. There is one interesting thing I mentioned in the previous lecture, that there are two ways you can do this these problems. One is two different boundary conditions. See, one is called the periodic boundary condition. Often called PBC. This was used, remember, in determining the Born-von Karman boundary condition, which was used to determine the allowed values of k when we found out the density of states. There is another which is called the open boundary condition, which is OBC, and these two give slightly different results for a finite system, and then those we will come back to at some point. But at the moment, let us consider a very large system, and therefore we do not have to bother about the boundary condition right at the moment, but I will mostly use the periodic boundary condition. So, what does periodic boundary condition entail? Okay, it basically means that you are using, for example, in one dimension, it's very simple. In one dimension, I just wrote this, I drew this lattice. Then periodic boundary condition means that the last lattice point has its nearest neighbor, the first one as well. So, one has to just fold this lattice. So, n plus 1, this is n plus 1 is the same as 1. So, that means u of n plus 1 is equal to u of 1 in this way of doing things. That means psi at n plus 1 will be equal to psi at 1 and psi 0. Okay, so let just I will use that one mostly. So, whereas if you have, this is PBC. In open boundary condition, of course, this is not true, which means that so let me just show you what this gives. So, OBC, remember that beyond n plus n there is nothing, and before number 1, site number 1 there is nothing. So, C0 equal to Cn plus 1, sorry, U0 equal to Un plus 1 would give me 0. Okay. Basically, there is nothing beyond n and before 1. So, these are the boundary conditions. This is the one I will be using most of the cases one uses that boundary condition, but for as I said, for finite system, of course, one has to consider the OBC. See, for example, in one dimension, this PBC basically means that you will you have this kind of a geometry. So, this is these are 6 points, 1, 2, 3, 4, 5, 6. Then so n capital N equal to 6. Then the U7 is same as U1. So, that is the periodic boundary condition. So, this so this is the periodic boundary condition. In PBC, you basically has to convert the one dimensional linear chain to a ring. So, that just gives the periodic boundary condition. In 2 dimension, of course, this can also be done. For example, for a square lattice or a lattice which is like this. Let me just do it for this kind of a lattice. Now, you have to align this with this boundary. These two boundaries have to be aligned, and these two boundaries have to be aligned, folded. So, if you fold it once from, say, if you fold this, then you will make a ring, make a tube. Okay. Now, if you fold it again, that means this top surface has to join the bottom surface, then it becomes a torus. So, that is the standard practice of doing it in 2 dimension. In 3 dimension, of course, the structure is you cannot think about the structure physically, but this is a general procedure by which one goes about doing writing down the periodic boundary condition. So, in up to 2 dimension it is possible to show it geometrically. Beyond that, you have to imagine that the surfaces have been tied together. Okay. So, that means electron going out of this basically enters this side, and electron going out from this bottom surface is basically entering through the top surface. So, that's basically what it means in the periodic boundary condition. So, let me just digress a little bit about the solution. Remember, the solution that we got was E equal to epsilon 0 minus twice t cosine theta. Now, this theta we said that we will determine theta from the boundary condition. And so, let us look at the, just for a simple case, let us look at the open boundary condition. So, in this case, for example, remember our solution. The solution was u of m at the mth site was a e to the power I m theta. I can also add the minus e to the power I m theta. Okay. So, this is the general solution for the for u sub m, and it obeys the so we will show the condition, the boundary condition that leads to the chosen values of theta. Okay. So, let us just put this boundary condition that u of 0 equal to u of n plus 1 equal to 0. Okay. So, C0, that means U0. So, U0 is A plus B, that has to be equal to 0. So, B equal to minus A. Then the solution U sub m is so the U sub m is A e to the power I m theta minus e to the power minus I m theta. So, twice I times A sine of m theta, okay, which I can write as just d sine m theta. Okay. So, this is my solution. Now, I also know that u of n plus 1 equal to 0, which immediately tells me that n plus 1 into theta has to be equal to k pi, where k is an integer, k is integer. Okay. That means theta equal to k pi by n plus 1. Okay. So, the solution therefore is E equal to epsilon naught minus 2t cosine k pi by n plus 1. Okay. 2 minus 2t cos k pi by n plus 1, and k being integer. So, this immediately identifies the solution, the values of the energies within the. Now, we can choose the Brillouin zone. First Brillouin zone, the k values, the integer values are to be chosen in such way that you, in one dimension, for example, the Brillouin zone is from minus pi by a to remember I took a equal to 1. So, if I have to put now if I want to put a in it, I will just multiply k into change k to k into a. So, a was taken to be 1. So, if in that unit I can actually drop this a here, and my Brillouin zone is from minus pi to plus pi, and all I will have to do is to choose values of k within this range. So, the spectrum is a, so suppose epsilon naught is 0, then the spectrum is minus 2t cos of this, so which is a cosine kind of spectrum. Okay. So, it is a cosine spectrum, generally looks like this and it is restricted between minus pi and plus pi. Remember another thing, that for very low values of k, for values of k which is much lower than n, capital N is huge, you actually restore cosine function is like a cosine theta can be expanded as 1 minus theta square by 2, and it is again a k square spectrum. So, at low k's, for very close to the gamma point, where at the bottom of the energy band, you will have the spectrum which looks still like a free particle. So, if you have a very low density of electrons, when you are only filling up to this part, then you are filled only up to say this, then the spectrum is very much like a free electron spectrum. The changes happen at a bit larger k, which means that for very low k values or very low density of electrons, you can treat this spectrum as a free particle spectrum. Remember, energy 0 of energy can be chosen as per your wish, as per your convenience. So, one can actually subtract any constant part from the energy, it just moves the entire energy band up and down. So, choosing epsilon 0 equal to 0 is not anything wrong. One can always subtract out a constant total energy from the energy, constant value from the total energy. Because the entire spectrum just moves up and down by addition of a constant. So, it really does not matter if your intention is to calculate the derivatives and higher derivatives of the energy and plotting the energy. So, this you can shift the 0 as per your wish, and then absorb this epsilon naught in that shift and make it to 0. So, this is how this is what open boundary condition, for example, gives. I will come back to the periodic boundary condition. I actually can leave it as a problem for you to do for PBC. So, all you have to do is you have to choose take the solution as um equal to e to the power I m theta again, and or plus b to the power minus I m theta, and so what you have to do is you have to choose u0 equal to u n and u n plus 1 equal to u1. So, these are the conditions you apply. You only basically you use this C0, this condition will give you the energy spectrum, and the spectrum will be such that n times theta equal to twice k times pi, where k is integer again. Okay. So, then theta equal to 2k pi by n. You can easily see this, right? u0 is m equal to 0, put m equal to 0, then put m equal to n, and just that will give you n theta equal to 2k pi. They have to be equal, and so that leads to this boundary condition. to this condition that n theta equal to 2 k pi. Okay. So this is what so this is OBC and this is PBC. Okay. For very large lattice, of course, this distinction is very small, but for finite lattices there is a distinction. You can actually check for yourself by plotting in a computer. Just go ahead and plot these two energy spectrum for take say n equal to 6 or 8 or 10, and then plot these energy levels. Do two things: take first n equal to even and also n equal to odd, and in both cases plot for with OBC and PBC and see how the energy spectrum looks like. Okay. So that will be a very beautiful exercise for you to do and see that the difference in a finite size system. Of course, if you go to the infinite size system, these differences don't matter much, and spacing between two energy levels is so small that they are you will have 10 to the power 23 energy levels within a distance of, as I said the previous day, the bandwidth, for example, in this case is from, again, epsilon naught equal to 0 I am setting. So from plus 2t to minus 2t. So the bandwidth is 4 times t. Now typical values of t in a material is about maybe half an electron volt to 0.1 electron volt to maximum 1 electron volt and so on. So this could be, say, even at the high energy level, high value of t, say 4 eV, for example, if I take if t is equal to 1 eV, and this bandwidth is to be divided by 10 to the power 23 to find the number of states, right. So you can imagine what the there are 10 to the power 23 states to be accommodated within these two values, plus 2t and minus 2t. So you can imagine how close these energy levels are, and that's again I said that if you have a filling which is somewhere if you filled up only up to this, suppose your EF is here, then by this argument that there are so large energy, so many energy levels, and they are so close to each other, you can realize that this is almost a gapless spectrum. Above EF there is another energy level within an extremely small proximity, so that means that there is almost no gap. On the other hand, for a discrete system, of course, suppose you had 6 atoms, of course you had you put 6, suppose you put 6 electrons, it will be exactly at the middle, and there will be a gap for the next level. So the gap will be basically the discreteness of the number of the system. So it's a finite size system. The system is discrete and finite. In that case, you will have a band gap by necessity, because the energy levels are spaced from each other. In a gap of 40, in a range of 40, you will have to place only 6 states, and you know how to place them because of this theta values that I have just calculated in the open and periodic boundary condition. In the open boundary condition, you can just check that there will be gaps between states. So a finite size system has a gap simply because of quantum mechanics, and for infinite system, of course, that gap is exceedingly small, and one treats them as gapless. So if you have your Fermi level somewhere inside the band, not at the top, then of course you will have a metallic system, which means there is no gap at the Fermi level. The other thing is that in some books you will find that psi is written as psi n. The solution psi that I wrote for Bloch in the Bloch theorem, psi k equal to e to the power I k dot r u k of r. There is another index n added. So some books use n k. This basically means that so that will be is your I k dot r u of n k of r. This n basically signifies that in plain terms, if you have say multiple orbitals, for example, if you are dealing with an atom which has multiple orbitals occupied, then these interorbital interactions may be small, or if there is a finite interorbital excitation, then you have to diagonalize a matrix which is not only just this number of sites, its dimension will be number of sites into the number of orbitals, because each site will contribute, say you are dealing with 1s and 2p. So each site will contribute two orbitals. So these n index then denotes how many orbitals were originally involved per site, and appropriately you will have one band, and then above that you will have so you will have one set of bands, then you will have another set of bands, and so this is suppose this band is completely full, then you will have a gap, and then this band is empty. So this is a case of a semiconductor. So n index basically tells you how many bands you will form. For in this example that we worked out, there was only one orbital considered per atom, so we had only one band. So see, the band can be either full or less than full. These here for example, if you had two orbitals considered, you will have two bands coming out of them, and then of course you can have the situation that your first the lower band is completely full, and then there is a gap, and then you have an upper band which is empty. So that is the recipe for having a semiconductor or an insulator. So this n index basically tells you how many bands you are dealing with, how many states you started with originally, and per atom or per unit cell, and then you will have to keep that index in your solution, but it is just additional bookkeeping, nothing more than that. The matrix dimension is larger, and you have to diagonalize that matrix again in the same way, and you will get the solutions of, and then you will get various bands. You can have 1, 2, 3, 4 and multiple bands in a system which has large number of atoms in its unit cell and large number of orbitals involved in it. Okay, so that's how the band structure works.